Let's start. So how did exam 1 go for the people that did exam 1? Was it, pardon? Someone said something. I usually, because no one says anything, we need to discussion, we need to keep it flowing. So was it easy, difficult? I hear the word easy, challenging, too long. Okay, that's why you came up to me and asked questions. Now I understand. Okay, yeah. So you should have enough time. Again, it's just a matter of, I'm not saying that you're not practicing, okay? But it's a matter of practice. Typically after 4 weeks, 5 weeks, you really get to understand how MATLAB works. Some students understand it because they have prior program experience, and some need some more time. There's a question over there.
Is the multiple choice part weighted the same as the function part?
No, I have to look into the number of points, how many points the multiple choice was versus the written part. But typically the written questions are more points than the multiple choice questions. So your total score is a combination of the two. Okay, so let's start today. I don't know if you've seen what happened in Boston. It's really terrible, so let's think about these people. Yeah, it's really terrible, this country, that these things happen. That's the only fortunate thing, like country, the Netherlands. Yeah, no one cares about it. So we only have 16 million people, and it's so small. If you explode a bomb, you'll explode entire Europe. Okay, so lecture 7 today. We will not cover chapter 5 of the book, okay? And there's reasons for that, and that is that in my viewpoint is that it's a useful chapter, but not right now, not at this point, where you're still trying to learn how to program. The chapter is a little disruptive, because it talks about binary calculations and etc. So that's for later, okay? But not for now. So today I will cover pages 240 to page 261 of the book, which is chapter 6, is lecture 7. And today we'll talk about finding the roots of a function. Because you're trying to figure out, why the heck do I need to learn MATLAB? And one thing you could do with MATLAB is, if you have some complicated function, fx is something, and you're trying to find that value of x for which the function itself is 0, you can use MATLAB very easy. You will get a direct solution. Instead of you having to do this numerically or analytically, MATLAB will give you the solution immediately. And you can do that in a number of different ways. And today I will cover 2 different ways, essentially. That's bracketing and the bisection method. This fixed point iteration that's covered in the book, but I will not ask any questions about that on an exam or a quiz, okay? So you can just take out of the pages out of your book, okay? Just remove them if you get confused, because there's still students that ask me questions like, because they forget, like, do I need to know this? And once you remove the pages, you forgot about it. It's easier for me, okay? So 2 methods to find the roots of a function. So again, a quiz question would be, what is it? What is a root of a function? What does that mean? Now, that is the value for x at which that function is 0. Okay? So we'll start with bracketing, and then we'll go to the bisection method, and hopefully you studied the script. So usually what I do, I start with a clear statement here, line 22, because I use MATLAB for other things, and you might in the future be using MATLAB for other things, and sometimes it's useful just to clear the entire memory. Okay, so with clear, you clear the memory. Okay, so now, and then I write here, imagine we have some function, y is fx, and we like to find those values of x for which y is 0. Okay, that is exactly what we're going to do today. Okay, so that procedure is called finding the roots of a function. So please do this correctly in a quiz, okay? Because I believe it's a question in quiz 2, believe it or not. So please do that correctly, that you know what is the root of a function. Okay. Now, in the mathematical literature, a lot of different procedures have been developed to numerically find the root of a function. Some functions you can do it analytically by setting the derivative to 0, for instance, or just solving it. In some cases, setting the derivative to 0, but you can solve that analytically, okay? But many functions that we use that are way more complicated, unfortunately we cannot do it that way. Okay, so we need to do this differently. Like imagine a function like this here. Y is x minus x to the power 1 over 3 minus 2. At what value of x is y 0? And it might not so easy to solve immediately, yeah, analytically. Yeah, this is not straightforward to find an analytical solution. So, what you can do, you have a calculator, if you have MATLAB, and what you do is you just put in all kind of different values of x, and you just calculate the value of y. Yeah, you just generate 10,000 different values of x with lint space between a minimum and a maximum value, and you just calculate the value of y. And then you get an idea what the root should be, what value of x. Now, we can illustrate an approach like this. On line 35, what I define is I define the function as an inline function. And inline is something that was covered in the last part of lecture 6, okay? So you should know what an inline function is. Inline is a routine in MATLAB built in that essentially calculates or defines the function. And in this case our function is x minus x to the power 1 over 3 minus 2. And why do I use the dot over here? Yes, so that I can use that function, I can exercise that function if I enter x as a vector or a matrix. That's why I use this dot here. If I don't use this dot here, then I can only use that function with a single value. So I can do the following. I just copy and paste this. So you see this becomes our new queen, by the way, in the Netherlands. You see him? So he has 2 brothers. This is a sad story, by the way. He has 2 brothers. And they're both way smarter than he is. Okay, a professor that I know very well has taught him a lot about water protection, water management, and that's how he goes all around the world, because these people need to do something in their life, yeah? But he's not so smart. So he has a brother, an older brother, his oldest brother actually. 1 year and 4 weeks ago he went skiing in Lech in Austria, and he ended up in an avalanche, and he was dead for 50 minutes. They reanimated him, and he's now in coma, in permanent coma essentially. So that's his brother. So this family has had a lot of trouble, but anyway, this is a big thing. So it says there, we still have 17 days to go before our new king, Willem-Alexander, will be getting his, will become king essentially. So that's just the Dutch news, okay? Don't worry about it. You guys have bigger things to worry about. So now we have our fun, okay? So this is our, I have to copy paste. Now I have a function here. It says function is fun, I call it fun, this is now become an inline function. Fun, input argument x is x minus x to the power 1 over 3 minus 2. So what I can do now is I can create some values of x, for instance like this, yeah, and I can just do fun x, and then I immediately have the corresponding y values of those x values from 0 to 10. Okay, and that's the reason I use the dot, because let's say we remove the dot, just to show that, this is because of all the comments I add. Let's remove that. Let's move here. Let's remove this dot. Now I go back to Skype. Okay, now again I have a function which is the same function, but there's no dot here. Okay, and I had my x values, and now I'm going to try to attempt this. And you see what MATLAB does? It says that it has a problem with m power. So m power means raising something to the power. It doesn't know what to do. Because we, as an input vector, we specify a vector, but we don't have vector calculation in our inline function. So we get a crash. Okay? And it's much easier to do vector calculation over scalar calculation, because obviously what I can do, I can write a loop where I first calculate fun 0, then fun 1, I calculate fun 2, I calculate fun 3, but it takes way more time. It's way easier if I just specify my function here so that I can calculate in vector operation. Now, let's see how this function looks like, because you're lost. You might be lost. You might not know how to find the root. Okay, so this is the question on exam 2, for instance. We give you a function and we ask you how many roots does this function have? And if you really don't know how to do that, then the easiest thing is just to plot that function first, yeah? So that's what I'm doing here. I create values here between 0 and 10. And because I don't specify a third input variable, automatically linspace knows we're going to have 100 values between 0 and 10. So now I have x, now I have all these x values. You see I have 100 x values now. Yeah, that's a vector. And now what I execute, I just calculate y. And now the third thing is I plot. And then I should have my function here. This is the function, okay? So you see, we have x between 0 and 10, and then we have the y values. And now, because I am, my contact lenses are old, I can't see very well anymore, so I need some help, yeah? So what we do, we just plot the horizontal line with 0, okay? So that we see at what value of x we cross the y-axis at 0. So the first thing I do is I'll add some labels. Looks nicer, yeah? Here, x value, y value, or fx value. And then I add a title, it's also nice, if that's what you want to do here. Yeah? And then let's plot, for convenience, we just plot a line here. I'll quickly copy paste this in here. So I have to do hold on, yeah. X min, okay. 0. X max is 10. So now I have my horizontal line in green. Okay. So now what you can see, how many roots does this function have? Yes, and yes, okay. So if you really don't know what to do, and the question is, how many roots does this function have? The minimum that you can do is just plot that function and look at it. Because MATLAB has a nice option here. If I push this button here, the zoom, I could just zoom in here. And I can zoom in more, I can zoom in more, I can zoom in more, I can zoom in more. And you see here that I'm getting really, you see what the root is. 3.5215 or so, yeah? That's where we cross the y-axis at 0. So this is after zooming in many times. For those that don't know how to program in exam 2, that's useful, okay? You can do it this way. So reset to original view. So we see that we very clearly have one root over here. Okay, so we go back to our script. So you can please read the comments, yeah, because that's all mentioned in here, okay? Now, but unfortunately, this is not really creative, yeah? Like if you write a computer program, you want the computer program to figure out what the root is, not doing it yourself by zooming in on a function, okay? So the simplest approach is bracketing. So what is bracketing? Is we divide the x-axis in equal intervals, and we define how many intervals we have, and then we look in what interval between what two intervals the sign of the function changes. Because if we go back to the original plot, here, the sign, that function sign, SIGN, is negative in this interval. Yeah? Because the y value is negative. Yeah? So if I can do that. I have my y values here. I can do the sine of y. And what you see a lot of 1s then. And what you see is that there's a point that it goes from -1 to 1. Which means that the function goes from negative to positive. So bracketing is an approach where we just divide the x-axis in a number of intervals. And the number of intervals we define a priori. And we just look from what interval to the next. Does the sign of the function change from negative to positive or from positive to negative? Because the function can also go down. And we can have a function with multiple roots. Yeah? Which means that you do that at multiple locations. Now that's essentially bracketing approach. So we can write a script that does exactly what we just talked about. And that's what we did here. This is a script called bracplot. And why is it called bracplot? Because it does bracketing and plotting at the same time. And so it's always useful to take function names that are meaningful. Okay? So function output argument is xb. And xb is the interval where the root lies. So that's some value and some other value. And then fun. So and then we get the name of the function. Fun is the inline function as input argument. Xmin is the minimum x value where you expect the root must lie between xmin and xmax. Okay, that's the interval that you study. And then we have nx. And nx is the number of intervals you like to use. If we use one interval, in this case, if we study between 0 and 10, then we study 0 and 10. So if we say that nx is 1, then xb likely is going to be 0 and 10. The root lies in that interval. If we use nx is 2, then we have between 0 and 5 and 5 and 10. We have two intervals, so the answer of xb is likely going to be 0 and 5 because the root is 3 point something. So the higher the value of nx, the higher the precision of the interval, yeah? Because you have smaller intervals. So it's always nice with a function to actually mention what that function does. So the function does, that's the second line, finds the subintervals on x that contain the sign change of fx. And that's a root in this case, yeah? And the synopsis is, how do we use this function? Now you can see that there's two ways we can use this function. We can use it with 3 input arguments and we can use it with 4 input arguments. If we don't specify an x value, it's the same as with linspace. Then we have a line here on 24, the first line of the function that says n argument in, that's a function built in MATLAB. And you just specify if n arg in is smaller than 4. So in other words, you only specified 3 input arguments. Then automatically say that nx is 20. So then you use 20 intervals. If you do specify 4 input arguments, then this is not true. This statement is not true. So your nx value will be used that you specified. Okay, I can read all the comments here, okay? Now, so this function here, it specifies what is the input values, and it specifies what's the output. So this is good practice. When you write a function, I don't expect you to do this on your exam, but when you become an experienced programmer, when you write a function, you write what that function does, what the input arguments are, like line 7. You see the input arguments are treated there. And output, what comes out of this function? Honestly, I've written functions like 8 years ago, 10 years ago, and at that time I wouldn't specify what actually the function did. So if I look at that function now, first of all I see that it was written by someone that was a really poor programmer, but that's what that's still true today. Okay, but it's really useful because you read that and you immediately know, okay, this function does this. And it's the same as with the help in MATLAB. If I ask for help brag plot, we can actually try that. Here, help. You can do help on your own functions. So now it needs to think for a while. You see? And what it returns is everything I wrote. And not that it's correct English or so, but it's just to show that MATLAB has the help function, yeah? So it will return everything up to your first statement. All the text up on your first statement, that's what it will return with help. So if I don't specify 4 input variables, so in other words I don't specify an nx value, then I only have 1, 2, 3 input variables, then this statement is true, and then automatically nx is set to 20, because nx is a value that needs to be known for this function to work. So then the first thing we do with bracketing is we define values of x. We already did this just previously 10 minutes ago, but we do this in the function now, where we say specify values of x and use 100. We don't have a third input argument here, so that means linspace will create 100 values between x min and x max. And x min and x max were 2 input arguments there on top. So those values are known, yeah? So this is known. So we now get a vector with xp values, which has 100 values. Then I have a statement here that says evaluate that function. Function evaluation fun, xp. And I believe that this is the same if you do. Okay? That's the same as what I did. So this is the same, does exactly the same thing, but this statement is a little bit more generic for later use. But essentially, I evaluate that inline function at the values of xp that I just created on line 30 that are between 0 and 10 in our case. And again, they're input arguments to this function. Then what I do is I plot the function here and I plot the horizontal line. So we've already done all that. So we end up with something like this. Okay? Now, then what we can do, we can actually change the labels a little bit if we want. We just use a crit. The function crit on means add a crit to our function, to our plot. So now we have a nice crit, and this could be useful because now we immediately see that the root is between 3 and 4. Yeah? That's where it crosses the y-axis at 0. So crit on is yet another function, yet another built-in utility of MATLAB that can be useful. Now, what is done now is for graphical output, okay? It's not so important, but we'll just go over it, is where we specify a box, and you will see the end result later on. Okay, so I just copy-paste this to the screen for now. And this is the important part here, is I have a for loop here. The size of the function, comma 2, like f was horizontal. Remember, 100 horizontal function values that correspond to x. So now what I do is I loop over all of them. I loop over all the function values, all the 100 one, minus 1. And there's a reason that we do minus 1, and we'll talk about that later. And what I state here is an if-else statement that says, if the sign of fk is not equal to the sign of fk plus 1, In other words, if my function value at xk is negative and my function value at xk plus 1 is positive, then I know I have a root, because the function crossed the y-axis at 0. The sign is changing. So if this statement is true, then I found a root, because that means that the function went from negative to positive, or from positive to negative. What I do here then, initially I define that NB is the number of roots, okay? And it's 0 when we start. In this loop I now define, if this is true, I found one root, so I update NB. The number of roots now is NB plus 1, so becomes 1. And what I store those function values in XB, where the root is found, that interval, and that is between xk and xk plus 1. And if I found that root, I can actually plot something nice, and that's where the y box and the C comes in, that was on top of the script, where I can plot a really nice, I've a filled area where I found the root. And I will illustrate how this works. If I run this function, we can just go back to our main script, lecture 7. So I've defined my function. This is my function, that's an inline function. I've defined that. Then I define my xmin and xmax, and I define that I want 10 intervals. So with 10 intervals, I have intervals between 0 and 1, 1 and 2, 2 and 3, 3 and 4, etc. And now I just execute my function by just running it this way. And hopefully something comes out. And this is what comes out. Okay, so we'll clear it here. This is the result that you're going to get. MATLAB found that in this interval somewhere is a root, and put a really nice box around it so that you can see yourself that there's a root there. And so what happens if I increase nx? What do you think happens if I make this, because now we use some value, I can use 100. What do you think happens to the size of that box? Yeah, so if I use 100, that box becomes much smaller because the intervals become smaller. So I have a for loop that loops over all the different y values that I calculated and just checks, is the sign of my function in interval at the left side equal to the right side? Is that true? Then I don't have a root. And that's in this entire interval, all these individual small intervals, the sign is negative. Until you hit this point over here, and what you see there is that the sign is changing. It becomes, from negative, it becomes positive. So what you have is you have a for statement, if I go to brag plot. So you have a for statement that loops over all the f values, the function values, and again size f, 2. Size gives you the size of the vector. And the size of a vector has two elements. That's the number of rows and number of columns. And f is a horizontal vector. So the size of f gives you a result 100. And we're not interested in 1. And that's why we specify size f, 2. Where you specify, I'm interested in the second output argument of size, 100. So we loop from 1 to 99. And why do we loop from 1 to 99? Because you see on the next line with the if statement that we compare the interval fk, which the first time is function value f1, with f2. If the function gets to 99, fk plus 1 becomes 100. And we don't have 101 function values. So that's why we have, on line 69, we have -1. So we run from 1 to 99 in the case that nx is 100. Now, obviously, it's possible that I use a function where I run this thing and I don't find a root at all. Which means that my NB value, as soon as I found a root, I update this NB value and I store the interval where that root lies in XB. But if I have a function without a root, NB will remain 0. Okay, and so the function returns at the end that if NB is 0, then it displays to the screen no bracket found. Check the Xmin and Xmax values, or maybe increase NX. It's possible that it's due to the fact that you just don't use the right number of intervals. Because you can have a function where, yeah, if you use insufficient number of intervals, you don't find the root. You can test that at home. Okay? Now, we can also have functions that have more. Like if I specify sine of x, then this function has more than one root. This goes up and down. This keeps crossing the y-axis. Now, we can check whether our brag plot works, because now we have a new function. And now I can specify, for instance, this as to be minus 2 times pi. Oh. And I specify xmax as 2 times pi, and just will do to start with 10 intervals. So what we get now is something like this, where we see that we look in the interval between minus 2 times pi and 2 times pi. And even though there are 5 roots really, we only see 3. And why don't we see the edges?
Because you go like incrementing like k and then k plus 1. So you get
Yes, exactly. There's no k0. We need one to the left or one to the right. So what you can do is you could say, you know what we do? We just add or subtract another, and we add 0.1 here. And what you see is that it now locates all of them. Because now you do have something to the left of minus 2 times pi. Because the interval now has become minus 2 times pi minus 0.1. And the upper interval is 2 times pi plus 0.1. So essentially, bracketing just divides the x interval into a number of predefined, or the x space into a number of predefined intervals. And it checks, is the sign at my current function values equal to the sign of my next function value? Like here, if I have this interval, then here my sign is negative, yeah? If here would be my next value, because this is my interval and here's my next value, the sign is negative as well. So we know there should not be a root in this interval. Here there's no root, no root. At one point you hit over there and you see a sign change. Because this value here and this value here of x, they have a different sign of y. This one is negative and this one is positive, because the function here is negative, the function here is positive. So this works, but you see sometimes you get really large intervals. That's what in XB. XB returns the intervals here. So between minus 6.38 and minus 4.96 we have one root. And that's what you see here. Minus 6 point something, minus 4 point something. So in this interval, that's XB, that's the vector that comes out. This is our first root, this is our second root, this is our third root, this is our fourth root, this is our fifth root. And these intervals are rather large. If you go back to your mathematics teacher, he's not going to be very happy with this, yeah? He wants a more accurate answer. So what you can do is you can just say, you know what, I don't use 10 nx values, I just use 1000. Now what you have is really small intervals, because if you use 1000 x values between minus x or the minimum and the maximum value of x, you have 1000 intervals now, so you make really small steps. So you get really small intervals. But now you need to do 1000 calculations, okay? So now XB, you see, these intervals are much smaller. The min and the max values. They've become much closer to each other because we use such a large number of intervals. And so these intervals become really small. So way more accurate. We can even make it 10,000 if you like, or 100,000. So this is what we get if we do 10,000. So it almost becomes really small. And now we look at XB, and you see that it's now, we're really sure that one root lies between minus 6.2836 and minus 6.2823. So this already becomes pretty accurate. But still, to do this, we needed 10,000 calculations. We first generated 10,000 x values with lint space. Then we generated 10,000 y values. And then we did the for loop for I is 1 or for k is 1 all the way to 9,999. So that's a lot of calculation. So that's not very efficient. And that's where another approach comes in, and that's called bisection. So this we will forget about this fixed point iteration because that's another method, but it's more analytical. So now we immediately go to the bisection method. The bisection method is very similar to the bracketing method. So we start with an initial interval here, x min, x max. We specify the function again, so we go back to our original function script that we used. Yeah, this was our inline function. So now I can do function 2 and I get my function value y. So I have the same input arguments, and what I specify, the fourth input argument is not the number of intervals, but it's the number of iterations. So there's one difference between bracketing and bisection, that in bracketing we use a fixed number of intervals, yeah, that we specify, nx. In this case, what we do, we start between x min and x max, and each time we have that interval. So let's go into bisection. So I have that opened here. So here, this is bisection method to find fx is 0. Input arguments are fun, the minimum value of x, the maximum value of x, and n is the number of iterations. And what comes out is an estimate of the root. So that's no longer an interval, but it's a single value. So bracketing gives an interval between one value and another value, and can give multiple of those intervals. This function gives you a single value. Now again, in this case, there's a statement here that says, if you did not specify the last input argument n, that means that the number of input arguments is smaller than 3, then n is 15. This should be 4, I think, yeah? Am I correct? Yeah. So, then what I do is I define I set A and B. It's very simple. I set A to be the minimum value of x, and I set B to be the maximum value of x. Would I do it this way? No. But the book does it this way. Just to make it easier and to be direct correspondence with the book. Okay? So I just say that my minimum value of x that I put in, let's say 0, that is now A. And my maximum value of x, which was an input argument, is equal to B. Then what I do, I calculate the function values at A and B. So now I have two function values. I have the function value if x min is 0, then I have the function value at A is 0, and I have the function value if x max is 10, then I have the function value at 10. So now I have two function values. Now I write a for loop here, and I loop from 1 to the number of iterations. And we specified that the default value is 15, but we can use any value we like. And what we do is the following, is we have our minimum value A and our maximum value B. Now what we do is we take the value in between A and B, exactly in the middle of the interval. Yeah? We calculate, we call that XM. So XM, this is essentially XM, XM is A plus B divided by 2. Okay? So that's the same. So I have A, 0, B is 10, I divide it by 2, so I'm halfway now, 5. Why do I do it the way that's on line 28? Because that's mathematically faster, numerically faster for MATLAB. That's for more experienced programmers. This is more difficult for MATLAB to calculate than this, believe it or not. So that's why we leave this out, but this is exactly the same statement. It's just numerically superior. It's faster and perhaps even more accurate. So we compute the midpoint between A and B. Then we calculate the function value at that midpoint. Okay, so what we have now is we have the function value at 0, we have the function value at 5, and we have the function value at 10. Now I have a statement here on line 34 that prints everything to the screen. What's going on? Okay, I print to the screen K is the iteration counter. So the first time I go in here, this was 1, then it becomes 2, 3, 4. Then I specify the value of A, I specify the value of XM, the value of B, and FM. Which is the function value associated with XM, and M means middle, half. Okay, now I have a simple statement that says, I have my function value at A, the lower bound, I have my function value at XM, and I have my function value here at B, the upper bound. I now compare the sign of A with the sign of B. Yeah? If both are the same, if both of the signs are the same at A and B, so both function values are positive, then we know automatically that that we have to look in the interval from the middle to B, that the root must be in that interval. Because here they're both positive, which means that the function theoretically might go through 0, but because the function values are both positive or both negative, there's no root likely here. It's either completely below the y-axis, y is 0, or completely above y is 0. So we're going to look at this other interval, the other part, and that's what I essentially say here. If the sign of Fm, that's the half interval between A and B, is equal to the sign of Fa, the lower bound, yeah, then what I do is I define that my new A value becomes my middle value. And I define that the associated function value of A is now the function value of Fm. So essentially, I started with A, middle, B. I know that the sign of this function value and the sign of this function value are identical. So I know the root must lie in this interval. So what now I do is I say this value Xm now becomes A. Yeah, and what I'm left with is with my new AB interval, which is now Xm and B. And that's what this does over here. If in the case the sign of A and the middle are not equal, then we know that the function must go through 0 here somewhere. And then what we define is that B now becomes XM. So now we're going to focus on the first part, the first half instead of the second half. That's what this if-else-end statement does for you. Now we can execute this, and so I have my function, this one, I execute this, and this is what is printed to the screen. Is here was K, was iteration number 1 through 15 or 20 probably here, yeah, 1 through 20, yeah, that's the first column here. Then here I need to go back and see what we specify there. We specify there that that's to be A, that's the value of A. So what happens to A? Initially it was 0, the middle value was 5, and the B value was 10. And this was the function value at the middle value, 5. Then, based on this first iteration, what we did is we figured out is that the function value is positive at x is 5 and the function value is positive at x is 10. But the function value is negative at x is 0. So the root must lie between 0 and 5. And that's what you see here, is that A stayed the same, but that our upper bound value b now became 5, equal to our former value of xm. Now the new iteration, the middle value becomes 2.5. And now we have a new interval between 0 and 5. And now we figure out, we continue making these steps. And at one point what you see is that you have converged because A and B are no longer changing. So now what you see here is that you have a value that's 3.5 to 138,519, something like that, or any of these values. That gives you an estimate, probably the middle one here. That's an estimate of the function value. And this is what the function value is here at the end, yeah? So this is the half. So this is A, half, B. Function value in the middle between A and B. And this is what you see where this is almost 0 now. This is minus 3.467 times 10 to the power minus 6. So that's really small. So again, bracketing is a method where you specify, so there's different methods in finding the roots of a function. We discussed two methods. That's bracketing. That just you specify a number of x intervals and you compare from one x value to the next. Does the function value, the sign of the function value change between those two x values? Then I know I have a root. Is that clear? The sign of a function, is it the sign, if the sign of a function is negative, then it's, for instance, minus. If the sign of a function is positive, then it becomes positive. So then the sign changed between two x values. And you just do that for all the different intervals. You compare them, all the different x values. That's bracketing. That returns a number of roots and their interval in which the roots lie, and that's xb. Now that's not really efficient, because if you want to have a very accurate estimate of the root, you need to use a lot of iterations. That's where we use 10,000, so 10,000 function calculations. And that's where this is a more efficient method, that's bisection, where we start out with the same interval between 0 and 10. Then what we do is we calculate the function value in the middle between the minimum and the maximum value that we specify. And we calculate, is the function value in the middle, is that positive? And is this function value positive? If that's both true, then we know that the root must lie over here. Or if they're both negative. But if this one is positive and this is negative, or this is negative and this is positive, then we know the root must lie here. So then what we do, then this middle value is now our new b value. So we have a new interval a and b, which is between 0 and 5, and half of that is 2.5. So now we have two intervals which are between 0 and 2.5, and 2.5 and 5. And again we do the same trick. The function value here, negative or positive here. And you compare, are they equal? Then we know the root must lie here. Are they not equal? We know the root must lie here. Then we have that interval again. And that's what you see happening here all the time. Where you see what's happening to your a and b values and how it converges. So initially between 0 and 10, the middle value is 5. And this is how you see how the middle value changes. And this is the corresponding function value. And that function value should go to 0. And ultimately we can check what the function xm, what comes out of this. And indeed you see that this approximation of the root x middle between a and b is almost 0. Okay? You can revisit these lectures online, yeah? You know that. So we'll continue on Wednesday, and on Friday we'll have a review section of chapter 6 and other stuff.